everything that we've been talking about with enthalpy has been pretty much in theory. Now, what we're going to do is turn our attentions to the more practical sides of enthalpy. How do we measure this in a laboratory? Well, the study of measuring heat changes is called calorimetry, and that's how we're going to show how delta E, delta H, and heat is all related to each other. So calorimetry is the study of heat changes, and the instrument that we use to measure heat changes is called a calorimeter. All right, now to understand how calorimetry works, we've got to look at two different topics: specific heat and heat capacity. So specific heat, let's take a look at that first. Okay, now some books will represent specific heat with a lowercase c. All right, I'm going to not do that because in the next chapter, when we start talking about quantum, lowercase c has a special connotation. So I'm not going to use lowercase c, but instead I'm going to use lowercase s. Okay. Now, so keep in mind, some books will call it lowercase s, some books will call it lowercase c. Just keep in mind when you're looking at different textbooks, just keep in mind that sometimes the letters can change. So specific heat is defined as the amount of heat required, not heart, heat, amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. Okay, and so that's how we define specific heat. It's the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. So the units that we use for specific heat will be joules per gram times degrees Celsius. Okay, so that's specific heat. Now, heat capacity, which we represent this with a capital C, heat capacity is defined as the amount of heat that's required to raise the temperature of a given quantity by 1 degree Celsius. And so its units is going to be joules per degree. Now, wait, Jim, you might be saying, okay, well, what's the difference between the two? Because this sounds pretty much like it, these sound pretty much the same. And they do, but here's the thing. Specific heat is talking about a specific mass. So you're taking 1 gram of the substance and trying to figure out how much heat is going to take that 1 gram to raise it up by 1 degree Celsius. Heat capacity, on the other hand, is talking about how much heat is it going to take everything and raise it by 1 degree. So when we're looking at the units, specific heat has a mass unit in the answer, in the units. Heat capacity does not. Okay. Now, is there a relationship between specific heat and heat capacity? Yes. And again, it's because of that mass unit. So here's the deal. If you take the specific heat, S, and if we multiply it by the mass, M, okay, so if you know the mass of your stuff, now, again, the units here for S is going to be joules per gram degrees Celsius. And if we multiply that by a mass, which is going to be in grams, the grams cancel out, so we're left with joules per degree Celsius, which is actually C, the heat capacity. So the equation that we use to relate the two, heat capacity with specific heat, is C, the heat capacity is equal to mass times the specific heat. All right, so that's how they're related. All right, now how do you relate heat and heat capacity and specific heat? Well, if we know the specific heat of and we know the mass of the substance, then we can actually calculate, we know the change in temperature. That will tell us how much heat has been absorbed or released in the process. So what we're going to do is now take specific heat and try to relate that to the actual heat that's evolved or emitted. Okay. So the way we do this is that we take Q, which again, that's heat. Okay. This is going to be equal to mass, M, times the specific heat, S, and we're going to multiply that by the change in temperature. So again, M is mass, and that's going to be measured in grams. S is specific heat, and that's going to be joules per gram degree Celsius. And then delta T is the change in temp. Okay. Now, delta T, to calculate that, you're going to take the final temperature minus the initial temperature. So whatever your final reading is, minus the initial reading. So we could rewrite this, if you need to, as Q is equal to MS times the final temperature minus the initial temperature, if that makes it a little easier. Now, we can also relate heat to the heat capacity. Remember that the heat capacity C is equal to mass times the specific heat. So in our equation, in our specific heat equation, you got MS. If you replace M times S with heat capacity, then you would get this, that heat is equal to the heat capacity, C, times delta T, which to me, I don't know, because I'm being silly, that almost looks like Q is equal to cat. If you treat the triangle as if it's an A, it almost looks like it almost spells cat. Okay. All right. So, hey, whatever you got to do to remember these things, you go with it. Now, keep in mind that the sign of Q is going to dictate whether or not a process is going to be exothermic or endothermic. All right. So I'll tell you what, let's try out a sample problem before we jump into a little bit more complicated one. So here's our problem. An iron bar of mass of 869 grams, okay, cools from 94 degrees Celsius to 5 degrees Celsius. Calculate the heat released in kilojoules by the metal. So you're already told that Q has to be negative. So that's kind of nice. Being told in the problem that heat released, because it's released, Q's got to be negative. This has to be exothermic. Now you're also told the mass. So let's write down what we know. Mass is 869 grams. The initial temperature is going to be 94 degrees Celsius. The final temperature is 5 degrees Celsius. Okay. So from those, we can calculate delta T. And then we know mass. We know the final and the initial temperatures. The only thing that we need is to find the heat, the specific heat. Now, what's really nice is that depending on your object, these are all constants. So you can actually look this up. And then right here in the next page of our notes, look, we've got a little chart here that has specific heats. And look at this. Here's iron. So the specific heat of iron is 0.444 joules per gram degree Celsius. So here we go. All right, so we got our information. So we're looking for Q. That's what we're looking for, but we're already told that it's going to be a negative value. Or if it doesn't come out to be negative, we got to make it negative. All right, so let's set this up. So Q is equal to MS delta T. Okay, let's pop in what we know. So the mass is 869 grams. S is going to be 0.444 joules per gram degree Celsius. The final temperature was 5 degrees Celsius. The initial temperature was 94 degrees Celsius. All right, so let's take care of the delta T part for a second. So if we take 5 and subtract 94 from it, 5 minus 94 gives us a negative 89 degrees Celsius. So this becomes 869 grams times 0.444 joules per gram degree Celsius times negative 89 degrees Celsius. Now, if you take a look at the units, though, this is kind of cool. Grams is going to cancel out with grams, and degrees Celsius is going to cancel out with degrees Celsius. The only unit that you're left with is joules, which is heat. That's Q. So that's perfect. All right, and look at this. The temperature actually has the negative value in it. It's already negative. So if we multiply all these values together, it's automatically going to come out to be negative. All right, so if you take 869 times 0.444 times negative 89, this gives you negative 34,339.40. And this is going to be joules. Now, the last thing that we got to do is that we're told that we need to convert this to kilojoules. So let's do that real quick. So if I divide this by 1,000 joules for every kilojoule, that value should be negative 34.3 kilojoules. And so there's your final answer. Okay, so in the next video, what we're going to do is take a look at how do we use the heat capacity and the specific heat and try to see the different types of calorimeters that we can use to solve for heat changes.